Hello, this is Alex from INDUCTA, and I'm happy to present a new feature, user-defined beam reinforcement in SLB software. There will be two videos in which we will demonstrate different ways that the beam design tool can be used. In this first video, I will show how to perform a new beam design and beam design optimization, and in the second video, I will show how to check existing beam reinforcement. These tutorials will cover all main concepts of the beam design tool and cover the full range of functionality. So let's open a simple SLB model with a 2-span beam. Let's mesh it, run the analysis, select the beam, navigate to results, beams, wide beams, envelope design. Upon opening the beam window, the software has designed the beam, and these results are shown by default as design reinforcement results. The design has been run using the design parameters as specified under material properties in SLB, namely N24 bar for bottom and top reinforcement, N12 bar as tie, and 44mm effective cover. The simplest and fastest way to input user-defined reinforcement is to convert the default design reinforcement. This can be done in one of two ways. We can either navigate to User Reinforcement tab and click Convert, or we can go straight to User Reinforcement Results. The software will recognize that there is no user-defined reinforcement yet in the model and will offer us to convert design reinforcement into user and run the capacity check. Let's agree. So what has happened? The software has picked the maximum designed reinforcement for top, bottom and ties for each span and has applied it to the entire span. The reinforcement is shown as double arrowed lines with label in the view, which from now on we will call user reinforcement intervals. The software has added 4 intervals for top and bottom reinforcement, N24, 2 N24 bars as bottom for the first span and second span, and also 2 N24 bars as top reinforcement for the first span and second span. Also, the software has added 2 N12s at 135mm center spacing ties for the first span and 2 N12s at 200mm center spacing for the second span. Selecting any beam section either in the results table or in the model view will show some summary. There are 3 labels in the top left corner of the model view. The top label will indicate whether it's envelope results or particular log combination results. The second label will show pass or fail label for the entire beam. And then the lowest label will show the pass or fail result for the selected section. We can toggle between design results and user reinforcement results either by using the buttons on the ribbon, design reinforcement, user reinforcement, or using the shortcut keys on the keyboard, D for design reinforcement and U for user reinforcement. The asterisk symbol next to the pass label indicates that there are detailing warnings for the entire beam and for the selected section as well. Also, this is indicated by yellow circles in the model view and the yellow background of the corresponding row in the results table. For the selected section, referring to the report, we can see that clause 861b spacing requirements may be violated. Currently we are looking at the envelope results, so only the summary is available. We can't yet explore the particular capacities and the detailed report for this section because capacities and 5 factors for bending depend on the particular loading. So the capacities only make sense in the context of a particular log combination. So to explore detailed reports, we should switch off envelope and focus on a particular load combination. I would like to stop here for a minute and explain in more detail why we do not produce envelope capacities for user-defined steel. As per item B of table 222 of AS 3600, safety factor for bending capacity depends on neutral axis parameter KUO, which is a function of the load combination. Also, as per clause 824, concrete shear capacity VUC depends on strain at mid-height of concrete section epsilon x through the KV parameter. So VUC is also a function of the load combination. Basically, the same reinforcement may provide different capacities for different load combinations, hence we cannot produce a single value for the envelope. We can only record the smallest safety factor and governing load combination, which we do, and this information is available from the results table when envelope is selected. Now, let's move on. For example, for the selected section, if we scroll down to the very bottom of the report, we can explore the detail and requirements, and what we can see from here is clause 861 tension phase reinforcement spacing is 312 mm, which exceeds the allowable 300 mm. What that means is the distance between the bottom bars, between the centers of the bottom bars is 312 mm, and we need to reduce that. One way to do so is to add a third bar for top and bottom both spans. Let's do that. There are several ways that we can add it user-defined reinforcement, and I'll show all of them. Firstly, we can select the interval, navigate to Properties tab on the right. Let's pin that so it does not disappear. From the Properties tab, we see that we have added 904 square millimeters of reinforcement, which is 2 N24s. However, we know that we need 3 bars. So let's change the number of bars to 3. Enter. Upon hitting enter, we'll lose the user reinforcement check results because we have modified the reinforcement and we have not rerun the check yet. So we can go to user reinforcement tab and click check update capacities, or hit F5, or if the auto recheck option is on, then the check will be rerun automatically every time any change is committed. However, it may become really slow for the large beams with a large number of sections, a large number of load combinations, so by default this option is off. So we have changed the number of bars to 3, and 3 N24s give us 1356 square millimeters, which is maybe too much for that section, as we remember 904 was enough. So let's also reduce the bar diameter to 20 millimeters, which gives us 942 millimeters squared, which is good. And to maintain the same clear cover, let's increase the effective cover to 42 millimeters. Let's modify other intervals as well. The other way to add reinforcement is to select the interval, right click, and choose edit user reinforcement from the context menu. So it's going to be 3 N20s at 42 millimeter effective cover. Apply. And a third way to add reinforcement, which we will apply to the top reinforcement, is to use user reinforcement editor on user reinforcement tab. Under top reinforcement table, let's also change the number of bars to 3 for both intervals. Change the diameter to 20 and effective cover to 42 and hit OK. Rerun the check and explore the results. So as we can see, all detailing warnings are gone now, and we can focus on optimizing this reinforcement now. It's evident that we don't need 3 N20s for top and bottom along the entire length of both spans. So we definitely can reduce the amount of reinforcement, of top reinforcement, in the middle of the spans and the amount of bottom reinforcement above the middle support. To do so, we will need to have more intervals. Let's do the top reinforcement first. Select the interval, right click and hit split. This will split the interval into two intervals at midpoint, maintaining the parameters. For reference, let's switch back to design reinforcement and leave the design moment on, so we know where our one interval should end and the other interval should start. Selecting the interval and dragging the control point will modify its extent. I'm modifying the locations of the interval such that we have larger amount of reinforcement above the support, which will provide enough capacity to cover the design moment above the middle support. And we can have less reinforcement along the mid spans. So for example, let's change the label as well. T1 will have 2 and 12s for the first span, and also that'll be T3, 2 and 12s for the right span, and I'll leave 3 and 20s above the support. I'll do the same for the bottom reinforcement. I'll split the interval and drag the extents. So we'll have larger amount of reinforcement to provide enough capacity for that bottom moment, and I'll have some smaller amount above the support where we have 0 design moment. I'll also change the label, say this interval will represent 2 and 12s. This will be B3 and it'll remain 3 and 20s. Same for the left span, B1, 3 and 20s. And let's rerun the capacity check. Switch the banding capacity on and look at the results again. So what we can see that now our beam fails for negative bending and additional tensile force caused by shear and torsion in the flexural compression side at the top of the section. The failure codes are mentioned in the report. So NB stands for negative bending and TCDT stands for additional tensile force at the top of the section. Also, there is a detailing warning on the leftmost section of the beam, which we will explore later. First, let's focus on negative bending. As we can see, the leftmost section of the beam has 97.8 kilonewton meters of bending moment. However, it's only 53.1 kilonewton meters affected bending capacity, so we're lacking reinforcement above the left support. Let's increase that. So I'll split the T1 interval again. I'll drag it a bit, its extent a bit closer to the support because we don't need it until the mid of the span, obviously. I'll change this label to, let's say, to T1I, and I'll bring the amount back to 3 and 20s there. And my T1B interval will keep the 2 and 12s. F5 to rerun the check. So we can see that the negative bending failure has been resolved. However, we still have the additional tensile force at the top of the section failure next to the right support. So this is also an indication that we're lacking reinforcement above the right support. Let's do the same thing. I'll split the rightmost top reinforcement interval in halves, adjust its position slightly, change the label for simplicity, T3B, it will have 3 N20s, and my T3I will keep 2 N12s. Reset the view, rerun the capacity. So the software tells us that the beam has passed all the checks with no failures and no detailing warnings. It is important to note that the software assumes that the reinforcement is fully developed at any point on the interval. Hence, we see this abrupt changes in the bending capacity where one interval stops and another interval ends, because the software does not consider development lengths and splices. So it assumes that the reinforcement is fully developed at any point of the interval. We have now optimized the longitudinal reinforcement design. Let's proceed to transverse reinforcement optimization. Let's hide the top reinforcement and bottom reinforcement and just focus on ties. Let's provide enough reinforcement rate as required by the design. If we go back to the design reinforcement results and click on the ASW button, which will give us the designed rate of transverse reinforcement, we can see that the largest rate which is required for the entire beam is 1458 millimeters squared per meter. Let's produce a single transverse reinforcement interval for the entire beam, which will provide enough reinforcement. How we can do that? I'll select one of the intervals, right click, delete, drag the extent of the remaining interval so it covers the entire beam length, and I'll provide at least 1458 millimeters squared per meter. To do so, we can, for example, have 3 legs of N12s at 200 centers, which will provide us with 1695 millimeters squared per meter rate. If we rerun the check again by hitting F5, the software will switch to user reinforcement results automatically, and it'll tell us that our beam passes all the checks, including the shear and torsion checks. We can also navigate to results, say shear capacity, reset the view to fit the diagram in, and compare the shear forces next to the shear capacity and torsion moments next to torsion capacity. Again, in some cases we may need to reset the view to fit the diagrams in the view. Obviously, further optimization of transverse reinforcement is possible. However, we can't go much above 200 millimeters, as this will violate the detailing requirement for torsional ties. So I think we can leave our design here. So in this example, I showed the main functionality of the user-defined beam reinforcement. We have designed the beam, we have converted the design reinforcement into user-defined reinforcement, and performed some optimization. Also, we had some failures during that process and detailing warnings, which we were able to successfully resolve. In the next tutorial, I will show you how to add user-defined reinforcement from scratch, as if it were an existing beam, an existing reinforcement, and perform the check. So stay with us, and thank you for watching.